This is going to be a video about the AVR64DD32 demo project, which is an application I wrote to demonstrate the features of the AVR64DD32 microprocessor. I'm going to break this project down into a lot of subsections for you, and the intent is to give you an in-depth overview of what the capabilities of the software are and how it interacts with the hardware. The demonstration code for this project is available on GitHub. The link will be in the description for this video. Sometimes I'll reorganize the GitHub repository, and so the links might move. Double check the video's description for the most accurate link. Let's start by demonstrating the application. This application is connected to the real world via USB connection connected to terminal emulation software. On the Mac I use Minicom, and in Windows I use either PuTTY or TerraTerm. The intent of the application is to have a menu displayed and active readings at the same time. The display itself is divided in half. The left side of the display is used for menus, while the right side of the display is used for readings of the different subsystems. The menu system has 3 levels. The top level is a command-driven menu where you type in a full command like ADC or DAC. The second menu is character-driven, where you enter in a single letter to invoke the menu command. This menu displays the configuration options for a given subsystem along with its current values. And lastly, the pop-up menu. The concept behind this menu is that you are presented with a list of options for a given parameter for you to select from. This menu is also a single character option to select the parameter. As stated earlier, on the right-hand side of the display are the values from the active subsystems. You can enable or disable any subsystem, and in doing so, you will update the screen accordingly. If enabled, a subsystem will appear in the list. If disabled, the disabled subsystem will be removed from the list on the next display update cycle. This holds true for changes to any parameter of any subsystem. Those changes are immediate, and they will appear on the next cycle of that subsystem's process. What I want to demonstrate is how the real-time processing of this particular application works, so you can see how the screen actually builds in slow motion. What I'm going to do is set a breakpoint at the top of the main monitoring system. And what we're going to do is run the application to that breakpoint and continue running to that breakpoint over and over again as you see the screen build. What you're going to see is the menu system processing monitor is going to be highlighted in pink. When it's in pink, what that means is that the CPU is running. And when it turns green, that means we've hit the breakpoint and we could do additional debugging if we so desired. Everything in this system is state machine driven. What that means is for a particular function, we're going to go through a series of steps in order to complete its task. Each system itself has its own set of tasks. That would be either the menu system or the display system, ADC, etc. So what's this going to mean as we build the display? You'll see items appear on the right-hand side of the screen, which is the readings area or the informational area. And the values that appear in that area will be 0 in the beginning until the individual system has had a chance to calculate or produce a value. While its state machine is going to gather that information, we're going to see what happens on the left-hand side of the screen. You're going to see that the left-hand side of the screen starts to build the main menu. As we continue going through the series of steps in order to build the entire display, you'll see that at some point in time, actual values will start appearing on the right-hand side of the screen. The purpose of this video is to review and explain how all the support modules work. I will cover the system initialization, the system monitors, the display driver, the menu system, and saving data to EEPROM. During this process, we're going to take a brief look at the ADC and DAC systems. The balance of the subsystems we will cover in detail in individual videos for that particular system. So before I start any project, I have to have design goals. And in this case, the main design goals are as follows. 1, no system holds up any process. There's always exceptions to the rule. In the case of the EEPROM, because of the nature of what it does, that's the only block of code that I'm going to stay into to make sure it gets completed because of the vulnerability of the system during that period of time. Because I'm holding up and talking directly to EEPROM, and that write process is critical. The other state machines I'll explain in more detail once we get to look at the individual subsystems. The second thing is everything is modular, so you can move code between applications. The code between the applications, because the hardware that's inside of the AVR64DD32 is unique to this processor, as it has each subsystem within this processor, making it modular between multiple processors is going to be rather difficult. However, making it modular between other AVR64DD32 projects is not. And so the goal is to have that code be transportable from one project within the microchip family to another. And the third area is to create an abstraction layer when possible between the environment and your code base. In this particular case, again, because the processor itself has hardware built into it, that's going to be a little difficult. But I'm going to show you in a minute other applications that I've done where the peripherals have been external to the microprocessor. And some of the modules in the 6502 project that I have built are independent from the processor, and those particular drivers would be created with an abstraction layer so that you can move them between other projects. Let me break this concept down graphically. There's 3 levels: the software driver, the hardware abstraction layer, and the physical hardware. What we're trying to show you is that the software driver is independent from any code base. The hardware abstraction layer is the translator between your software driver and the physical hardware. And then the physical hardware is the hardware that is connected to the pins of the microprocessor. So the hardware abstraction layer gets a command like lower chip select, and what it then knows what to do is to set the appropriate pin. Now here's an example of the code. This particular software is a read monitor, and it's going to communicate to an AC device that's external to the microprocessor. And in order to communicate with it, you have to drop chip select low. So you can see in the read state set CS section that we're dropping the chip select low. I got that information from the data sheet on the particular chip that we're talking to. And it shows you that the first part of the sequence is the drop chip select. I pulled this code from temp code that I'm working on so that you can see what I'm referring to. Here you have the ADC chip select 1, and that is connected to PC0. And then you'll see that PC0 is defined by a 0x01. Then if we go off to the initialization code, you'll see that I then configure the ADC chip select 1 directly to the port C DIR set. And then when I go to activate that, you'll see that I have a block of code here that then flips the bit in the appropriate position depending upon the calling code. As far as the software driver goes, anytime it wants to talk to ADC chip select 1, it uses its internal name. However, the code at the hardware abstraction layer knows to translate that to the correct port pin assigned to that. And that's how we are able to take the software from one project to another by just changing the defined attributes of where the actual hardware pin is connected to that particular device. Demo project system initialization. So the first thing I do when I start a new project is to initialize the hardware. So as you can see in the main here, I have the atmel start init, and I got this code from the wizard that created the project, and this is going to initialize the processor to a known state. After that, I have all the initialization routines that I'm using for the individual hardware subsystems that I'm using in this particular project. So now what we're looking at is the simplest form of the initializer. In this case, I'm just initializing the output pins for the DAC, followed by some reinitialization code. Reinitialization code is code that I'm going to call over and over again after I do a save or change to the configuration, which is then stored in EEPROM. And we'll take a look at how that's used in a little bit. So the next thing I'm going to do is set up the display processor map. So the display processor map is a structure and the variable is item. What I'm doing is populating that particular structure with values. We'll cover those values and what they do when I discuss the display processor. I like using data structures because the data structures allow me to manage all this elements of information in a single pointer to a variable that then gets set into the system. So if I want to increase or add an additional item to the structure of data, it's simple for me to code. So the next thing let's look at is the reinitialization code. The first thing we're going to do is load the configuration data from E². Now this function could be called whether we're loading it from the first time or we're loading it after we've made a change to the menu. So the purpose of this is to get the latest code. The next thing we're going to do is to apply the configuration information to the, in this case, DAC system, which is only changing the reference voltage. Other systems may be more complex than this. The next thing I see here is that we're enabling the DAC as an output. This code doesn't really belong in the reinitialization code. It should be in the initialization code because we only need to call it once. What we need to do next is to reinitialize the state machine. The state machine is the code that sets up the hardware and determines what the output's going to be as far as the values go. So this now completes the DAC initialization and reinitialization code. So let's look at the ADC code. This is a little more complex, as it's actually three systems in one. There are three systems: instant, average, and differential. In my code, I'm monitoring three different I/O pins. And as you can see here, I created enumerated values, so it's easy for me to read in the configuration data the different channel names. So let's look at the ADC configuration. So let's take a look at how the system is architected. The ADC process engine is a structure. I like using structures because it allows me to contain all the information in one area that will be applicable to any subsystem or anything I'm working with. It doesn't have to be related to this particular subsystem. So the first thing we're going to take a look at is the ADC configuration. The ADC configuration has got a signature byte, the ADC channel name, whether it's enabled, and a host of other variables that are used to set up the ADC channel itself. Now I use a signature byte, that way I know when I'm looking at EEPROM that I'm looking at the right set of data. As you can see, the signature byte is described in an enum that each system has a unique number. That way, when we look at comparing the values in EEPROM later on, we'll know that we're talking about the right channel. So the channel name is going to be used to describe the type of channel we're working with. As you recall, a minute ago, I mentioned that there were three types of channels currently in the system: instant, average, and differential. The balance of the parameters are used to configure the individual ADC channel. The enable will be used to turn on and off the readings. So now that we covered the configuration structure, we have the ADC results, the display value, and the display message. These are going to be variables that are used in real time, and they're going to be published when we initialize the system with the proper information that will be displayed in the screen, as well as anytime there is a result, we're going to store the results in that particular results that will be then pulled out later for use. So just a side note, what I'm basically saying is this data structure is twofold, one for configuration to start the system up and get it running and to track what's going on. And the second is to store real-time data that I'm going to pull back later to be used in the processing of the particular subsystem. What you're looking at here is the initialization code for the ADC process engine for all three channels. I'm going to break this down for you because the first half of this is going to be configuration, and the second half of this is going to be the default values and pointers to the functions that will be processing the information that is collected. What's highlighted now is the configuration options. So you have the ADC, the name of the channel, true, which was the enabled, and then you have the default settings for the individual ADC configurations that set up the individual channel. As I mentioned a moment ago, the configuration is two-way. I either use information or store information. In the case of the function pointers, I'm going to use that information. In the case of the ADC results display value and display message, I'm going to use that information to store the information for live data. So what you're looking at is I have preset the start information with zeros for both the ADC value and the display value. The instant message, average, and differential is hard-coded in the structure, and that will be used to display which channel I'm operating on. So let's take a harder look at the function pointers. Each system is unique, so whether it's instant, average, or differential, it's got its own set of ways of dealing with the information that it's collecting from the ADC system. So what I've created is a way of calling the individual function pointers for initialization, read, and display, so that way when I'm on a particular channel, I can get to that particular function code. And here is the pointers to those functions. So you have the initialization for instant, the initialization for average, the initialization for differential, as well as the read instant, read average, and read differential, as well as the display instant, display average, and differential are hard-coded into that structure. Let's walk through the ADC initialization code. So just as a reminder, you see that we have the process engine that's been predefined with the three different systems for configuration. When we look at the initialization code, you're going to see that we're going to set up the state machine, and then we're going to walk through the number of channels one at a time and load the configuration information. We're going to get that from EEPROM and store that into our data structure. And that will be used later on when we go to configure the systems. Then we're going to set up pointers to the different data elements that are going to be needed. One is the pointer to the data for the configuration. One's going to be pointing to the display processing code where it's going to display the information on the screen. It's going to set up the message and whether it's enabled. It's going to get that information from that configuration structure. And then it's going to post that to the display processing engine itself. So how do I make all this work with a single monitor function? Well, that comes back to these function pointers. So what's going to happen is the monitor goes through its system itself, it's got these reference pointers that it's going to call to for the individual functions. The monitor system itself doesn't know what it's calling, it just knows it has a pointer to a function. So it's going to ultimately, depending upon which stage of the initialization code it's in, call one of these functions that we've got highlighted on the screen, whether it's the initialization code, the read code, or the display code. So when you start the initialization itself, the first thing it does is check to make sure that there's no corruption going on and the pointer is a valid pointer. And what it's going to do is it's going to point to that memory location which is pointed to by the configuration for the initialization of that particular subsystem. So in this particular case, as we walk through the system, you're going to see that we're going to call the ADC instant initialization code. One other thing to really note here too is that there is a process engine index, and that's how the state machine keeps track of what it's talking to, or what system it's talking to is based on that index. So it's going to walk through each one of those stages one at a time until it gets through all three indexes, and then it's going to keep repeating itself. So what I want to do is to show you a quick demo of the function pointers within a monitor, and so you can see how that's going to work in real time. So what I've done is I'm going to set a breakpoint at this line of code here, which is the ADC instant initialization code. Now I'm coming down to the initialization function. I'm going to set a breakpoint there as well. So that's past the valid function pointer, and it's going to end up calling into the function pointer that's in the configuration data. So I'm going to start the debugging. And now I've hit the breakpoint. What I'm going to do now is to show you a couple of things. One is I'm going to add to the watch window the structure that we're currently looking at, which is all three channels. And when I highlight it, you'll see that there's the systems, all three of them are there. The other thing to note is you'll see there's valid pointers for the functions for initialization, read, and display. So it's not 0. That's how we were able to get beyond the line of checking for a null. And as you can see in the configuration information, there's the pointer to the name of the function that we're going to end up getting to, which was the ADC initialize instant. Now I'm going to single step into this particular function pointer. And as you can see, I've entered into the ADC initialization instant. So let me summarize. Basically, I used a structure that was defined with all the information I was looking to process and keep states. Then I had a loop that talked about the three different indexes for the three different subsystems. And then I taught the monitor that there were three systems, and it uses that index pointer to walk through each one. So I could expand upon the ADC system and add more support for additional ADC channels just by increasing the configuration settings and adding the additional functions for supporting the new channels that you're adding. So let's look at the display engine. The first thing we're going to look at is the configuration, which is a structure. It's got a pointer to the function where we're going to pass in data and a message. It's got a pointer to the data structure for configuration. It also has a pointer to a message and whether it's enabled or not. The entire display system is made up an array of the number of elements that you have defined as max number display processors. And then what we have is a state machine, which really basically only has a couple of states. Then we have three variables: index, slot, and row. Slot is used when you add an element to the array. It's the next slot where the data is going to be stored. Row is the current row that is being displayed on the screen. And index is used by the display monitor to point to which element of the display we're currently working with. So here's the display monitor code. It's broken into two states: display processor state print and display processor state loop. The print is where the print is going to happen on the display. And the row will be printed, that's where it's going to place the cursor, followed by a call to the function pointer that's going to connect to the display routine that was set up in the initialization. And in doing so, it's going to pass along a couple of arguments, the pointer to configuration, as well as the display message. So here's a copy of the code for the ADC display. This is also the function that caused the expansion of additional information that's going to be passed in from the display processing engine, because it needed to understand the three different systems. In order to do so, an additional argument needed to be passed in. And that argument is the pointer to MSG, the message. So what's going to happen is, if the enable is set, it'll process the code. If the enable is not set, it's just going to exit. Nothing will be displayed on the screen. When you look at the code itself, the next thing it's going to do is set up the color, which is the background, foreground color, and then it's going to print the message. And the message has got the ADC, and the capital S is going to be displaying the message. And that's important to know because the function I'm calling is printf_p, and the capital S means that value is coming from EEPROM as opposed to from RAM. If it was a lowercase s, we would know it's coming from RAM. So in this case, it's a pointer to a EEPROM value, which we stored earlier. So the next thing we're going to do is then display the value and the results that we had stored in the configuration package, in this case for the ADC. That's why a pointer is being sent into here from the actual data that we're working with for this particular function. So once we know that value, we can then publish this particular string and display that information on the screen. Then after we return from processing the displaying, and on the next state, we're going to come down and we're going to take a look to see if we've hit the bottom of the list for the display processor or not. And if so, we're going to start back to 0 and repeat the process over and over again until we get back to 0. And this is the loop that's going to be displayed on the screen for you. When I was demonstrating the code for the DAC or the ADC, it called a display processor add. This is when you pass in the structure. And what this guy's going to do is he's going to go and take that slot and figure out the next position and store all the arguments that were being passed in from the calling function. Again, these will be used later on. At the very bottom, you see we increment the slot so that way it knows where to store the next set of data. Anytime a subsystem saves data, that calling function is going to call this display processor set enable flag. It's going to pass in a pointer to its configuration and whether the enable flag has been set or cleared. What this code's going to do is it's going to walk through its array to find their match for the pointer to the configuration. And once it finds it, it's going to set the enable bit or clear the enable bit for that display mapped element. Then what's going to happen is that when the display processing engine goes through its loop, it's going to see that that configuration element is either enabled or disabled. If it's enabled, it's going to continue to process and print that element. And you'll notice that the display row is incremented. So if two elements that were already in the array are not enabled, they won't be displayed on the screen because they'll never get to this code. That's how the right-hand side of the screen can be maintained when you disable an element, that it disappears immediately. Also, in case the state machines are out of sync, which they can easily be with the ADC or whatever processing subsystem you're doing, getting into the ADC, in this example, where you see its own configuration, it's going to know that it's disabled and bypass the code. So you need two levels of verification so that the right-hand side of the display area, is not going to get trampled on by some other element. So in summary, the display engine is nothing more than a fixed array that has arguments being passed in. It knows its size based upon the number of slots that have been filled. The menu system. The menu system is made up of three unique sections: the menu header, the menu body, and the data entry. So first, let's go over the menu header. So the top of the screen will be where the menu header appears, and that's going to be the name of the current menu that you are in. So the way the menu header works is there's a structure called menu header. It allows you to set the row, the column, the theme, the pointer to the message, and the message size. The header code has some features / rules. When the column equals 0, if the text size is equal to 1, then the characters are repeated across the entire screen of the terminal to the terminal max column size. Else, the text is evaluated and is centered on the screen, which saves time and you trying to compute what the center of the screen is going to be. So here's the actual code. As you can see, if the column is equal to 0 and the max size of the character is 1, then we're going to follow the code that starts off by repeating it. Else, we're going to go through and try to center that particular text string in the center of the screen. So we have the message equal here, which is a single character. And it calls a macro, which is called make string with size. And if we take a look at the macro, what it's doing is it's taking the pointer that's passed in and it's determining the length of the string. And then later on, when we look at the menu item being used, you'll see that its message underscore equal underscore length now contains the size of that particular string. And you'll see that I've used the underscore length in a number of places. So now here's the actual data, and you can see that the column is 0. We have our theme, we have our string, and then we have the string length. And then, of course, when the menu engine processes it, it looks at all those bits of information being sent along in order to determine what it's going to do. So themes. I found that when I was starting to code that I had a sequence of color schemes that I seemed to use, so I thought I would create a structure called themes. And then what I did was I created a list of themes that were going to be popular. And so I just referenced them and I don't have to worry about setting the foreground and background color. So now let's talk about the main body section. So right below the header is going to be the main body section. And this is going to take two forms. One is going to be a command driven where you have to type in the command like ADC. And the other is going to be character driven, and I'll cover them independently. So for right now, what we're looking at is the main body of the main menu. And a couple of things that you're going to note here is that the main body, just like the header has a row, has a column, has a theme, and it has a message and a message size. But in addition to that, it's got a description, and then the pointer to the menu of where it's going to go. So in the main menu, you see you have all the support menus for ADC, CCL, etc. So those are the names of the functions that we're going to call when that particular command is executed. There's a lot of rules in the menu processing system. And one of them is that the data entry in this particular menu is set at null, which means there's no lookup data for it to find. The second thing is that's also important here is there's a mode called data entry menu, and that's telling it, the menu processor, that this is a top level menu. So in the configuration information, you have your messages that are your commands, and those are displayed on the left-hand side. Then in configuration, you have the descriptions, and the descriptions are displayed on the right-hand side. So now let's review the character-driven selection. As you can see in this menu, we have characters on the left-hand side, followed by a description, followed by a value. So how does that work? So what you're looking at is a split screen. On the right-hand side is the actual menu. On the left-hand side is the configuration that makes up that menu. You'll notice that there are messages called letters A, B, C, and D. You see them on the left-hand side of the menu, followed by the message enable, ref range, etc. Those are the descriptions now, and then you see them in the description section. Lastly, you see on the right-hand side the actual values. Those values are coming from the data entry section where the main menu knows to look them up based upon some configuration information that I'm going to show you in a second. So what you have the ability to do here is position and create a theme for the data being displayed from the data entry section. The menu system provides for a lot of flexibility. First, it has a function where it's going to call when the user selects the letter. For an example, if they select A, it's going to go to the enable/disabled main menu function. Now, how does it know whether it's enabled or disabled? That information comes from the data entry area. If you take a look at row 5, you'll also see that the data entry has a row 5. So the menu processor knows that the information it needs from the configuration body is going to get it from the data entry section, and it matches up the row number. And inside the data entry section, you're going to see that there's an offset to the location where that value is stored. It's also going to have a field type, and it's also going to have a decoding section where it's going to call to decode that. So the main menu knows to go to the decoder with a value, in this case, ADC configuration enable, and it's going to pass it into that, and that's how that information is going to get displayed on the screen. So now let's take a look at the data entry structure itself. So just like the other menu structures, it's got the row and column and theme. But the key here is it's now got additional information of the offset into the configuration data, the data type, and the pointer to the function, which is the decoder. So as you can see in the ADC configuration, you have your row, your column, your theme, followed by your offset to where the data is stored, followed by your data type, and followed by your decoder. So let's follow the reference range as a more complicated example. So the user selected option B, which then the main menu will call the reference decoder. So the reference decode is going to get a pointer that points to the data, and we're going to translate that data into a value, and then we're going to set it into a function called lookup vref by value. So the reference decoder is going to then call a common function that's a macro called lookup vref by value. In there, there's going to be an enumeration to the type of drop-down menu it is called drop-down vref, and it's going to convert the value into a 16-bit, and that was done to maintain compatibility across all the different data types. So it calls this common function and passing in the drop-down ID. And what's going to happen next is it's going to go do a lookup based upon the drop-down ID to get a pointer to that menu. I like things data-driven, and so that way you can add and expand data at will. And so by having the ID, it's going to go look up that ID and get that pointer that we need to work on. And then it's going to pass it on to a function with that pointer and the value to perform some action. And we'll take a look at that in a second. For the moment, I'm going to jump to the end of the story. And what I'm going to show you is that the value being passed in is from the data entry, vref data entry. So you see the values there that start off with vref, ref cell 1v024, etc., all the way down that column. That's the value being passed in. And what we're going to do is we're going to look up in this section of data, which is the data entry section, and find its row number. So for example, if we were 4v096, that's going to be row 10. Then we're going to go back to the vref body, and we're going to look at row 10 there, and we're going to find our string. And that's the string that's going to be ultimately returned back through all the processes back to be displayed in the menu. Now let's jump back to how the lookup menu worked. We passed in the argument called dropdown vref. And we go into the table, we see that the vref is assigned to the menu system called vref main menu system. We're going to return that pointer back, and we're going to use that pointer, which is going to point to the data elements that we're looking for. So let's look at the code now that breaks that down. So the top half of the section is designed to take the current value and look up the row number. And once it finds its row number, it returns that value into index. So as long as the value being returned is not a -1, it's then going to look through the top half, the section, which is the menu body that we're looking for, read one row at a time, trying to find the row number that matches the index that we had returned. So in this case, it was 10. Once it finds 10, it's going to return the string associated with that. Because the information we're looking for is actually stored in code, there's a function here called menu_body_read. And what this function is going to do is it's going to read from the code and get the value that we're looking for to be returned. So now that we have the pointer to the description that we want to return or display on the screen, this is going to then get sent back throughout the system, and it's going to be printed on the screen for you to see the resulting value. So let me summarize. There are three different types of menu structures. The main menu, which is command-driven, the configuration menu, which is letter-driven or single character-driven, and pop-up menus, which are also single character-driven. All menus are based upon three different elements: the menu header, the menu body, and in most cases, the menu data. All of the menu data and body are coordinated together through lookup functions for you to be able to read information and look up information for the decoding purposes or for the selection purposes. The menu engine is where all the complexity gets resolved and allows you to just generate tables to formulate the data that you're looking for. Saying all that, if you try to come up with a menu that is different than any of the other ones I've created, you'll have to create your own decode functions as well as pop-up menus in order to generate the additional information you're looking for. All those examples have been provided. So the next thing we're going to start to look at is the actual menu processor itself. Before I do a code walkthrough, what I want to do is break down the layout of the screen. The screen header code is going to appear at the top, and so we're using row and column. We're able to position everything one at a time. Then we're going to follow by the printing of the menu body, which will appear on the left-hand side. And then in the center of the screen, as you can see here, will be the data entry side. The menu processing engine. So the first thing we need to do is to initialize the menu processor. When we look at the code, it's just simply setting the state machine into an idle position. The next thing we're going to do is we're going to call main initialize because we have to give the processing engine something to do. And you'll see that the display main menu passes in a null into a function called display menu. And it's got a constant car message there, but it's never being used. The reason for that is if you take a look at the menu body where the calling of a menu is going to take place, you'll see that there is an argument being passed in with that function pointer. So in order to maintain compatibility from the top level menu, a null is passed in to that as an argument. And I'll cover more about that function pointer and the arguments being passed later on in this section. So anytime we want to change a menu, we set the active menu and pass in the argument or the pointer to the function. So as you can see, the set active menu is going to take the pointer being passed in and set that as the active menu and then tell the menu display to redisplay that menu. Now there's one caveat here, and that is if it's a drop-down, we're in a special mode. And a drop-down is a temporary menu that's going to appear and then disappear. So in that case, what we want to do is to take the menu that was the primary menu that we called from to call the drop-down, and we want to recall that after we have closed the drop-down menu out. And so that's what the code is that you're seeing here. So then we call the menu display menu. Then the very first command you'll see is set command mode, and I'll talk about what that does in a little bit. Then it looks to see if the active menu pointer is valid, and if so, it resets the system menu processing state machine, so it will start processing the menu. So now let's look at the states that make up the state machine for the menu system. The first state is idle. When the monitor comes into the idle, there's nothing to do, it's just going to exit. Then once we have something that we want to display, it'll start, and we'll review each one of these sections in a minute. But if you look at the structure, we have the header, we have the body, and the data entry. And each one of those sections have, let's say if we look at the header, it has a header and header test, body, body test, and data entry test. And what those are, those underscore tests, are how we determine whether we have completed that section or not. And then at last, we have the display of the prompt. So now let's look at the code that makes up the state machine itself. So as you can see, the idle state is just enters the monitor and exits. It doesn't perform any action. So there's one sidebar to note here. There is a status returned value. When a system is being processed and it doesn't know that it's in the middle of a menu or not, it's going to check this menu process status. And if we're not in the idle state, it's going to return a false. That way, the state machine in some other process is going to wait until the menu is finished before it attempts to change a menu. So now that we started the process of the start, the first thing it's going to do is make sure there is a header. And if there is no header, it's going to jump to the body. Otherwise, it's going to start positioning the information on the screen, turns the cursor off so you don't see the cursor float, and then it's going to take a look to see what kind of menu it is. So if the menu type is a drop-down or data entry, it's going to be an overlay type of menu, and it's not going to want to clear the screen. All other menus are going to clear the screen before it attempts to print it out. Then it's going to set up the next state, which is the header, and reset the value for the row pointer for the header data. So this compiler treats code differently than memory. And what it did originally was to place the menus relocated into RAM and wanted to use them from there. Unfortunately, the RAM is very limited, so what I had the compiler do is to put the menus in code space. In order to be able to use the menus without wasting all the memory, was I have to have a function called menu header read. And what that does is it goes to the code and copies that data into a local memory variable. The header code has some features / rules. When the column equals 0, if the text size is equal to 1, then the characters are repeated across the entire screen of the terminal to the terminal max column size. Else, the text is evaluated and is centered on the screen, which saves time and you trying to compute what the center of the screen is going to be. So here's the actual code. As you can see, if the column is equal to 0 and the max size of the character is 1, then we're going to follow the code that starts off by repeating it. Else, we're going to go through and try to center that particular text string in the center of the screen. So the menu data loops, we're going to do the one for the header at the moment. So when we look at the header itself, you'll see that this is an example of the ADC header, and there's 3 elements in the array. And what we're going to do is those elements are in a block of data called the ADC configuration menu. And you're going to see that each section, the header, the size, the body, the size, the data entry, and the size are outlined there. And that is the data packet that's going to ultimately be sent to the menu engine. And so the menu engine has its reference information that it's going to need to work with. So in particular for the header, we have the header size that's been stored by the compiler into that header size section. So now when we walk through the test of the ADC menu, we're going to come to this and we're going to look to see if we've hit the limit of the test or not. And if we have hit the limit of test, we're going to reset the elements and go to the next section, which is the body section. And if we haven't hit that particular minute. We're going to then go back to the top of the state, which is the header again, and keep this process going between the state header and the state header test until we reach the end, and then we're going to move on to the body. So an important note, anytime you're dealing with function pointers, you always need to test for null value in case the data is corrupt. And if this would be corrupt, then it's going to jump to the display prompt to continue. Otherwise, after we've completed our loop, we're going to end up going to the state body. Now let's take a look at the menu processor, the body state. So display on the screen, the way the engine works is we had the header that got printed at the top, and then the body is going to be the one that's now highlighted with the red box, and that's going to be filled in because we know the coordinates of the row and the column. So we're going to walk through the engine by looking at the body size, and then go through one line at a time like we did in the other systems, and print that particular line of code on the screen. So the first thing it does is it's going to read the data from the configuration, which was stored in code, and it's going to bring it into a local variable. And then it's going to display the theme, it's going to set up the row and column, and then it's going to print the data. And then it's going to move on to the body state, where it's going to test to see if we've completed the list of objects that we want to print to the screen. So once we've processed the displaying of the entire list, we come down to this section where it talks about data entry mode. So currently there are 4 data entry mode types: menu, display data, drop down, and enter value. And you control that by how you set up the menu structure itself. So the main menu you see has got data entry mode menu. Now in this example of the menu structure, this one has display data. So the display menu is going to automatically just jump to the prompt, and it's going to skip the data entry portion itself. In the current section that we're working on for the ADC configuration, we do have a data entry, so we're now going to jump onto or into the data entry section of the menu processor. The way all the data lines up is going to be by the row and column number. We already know that the enable was displayed on row 5 in position 2. And we also know that we're going to display the configuration information, whether it was enabled or disabled, because we know that's on row 5, and it's going to start at line 32. In the data processing engine, just like we've done in the other 2 engines, we're going to read the data from code into memory variable, and then we're going to start processing its position and color. Then what we have is we're going to look to see if there's a function. This function pointer is going to point to the decoder that will decode and display the information on the screen. And once we've done that, we're going to go on to the data entry test, where we're going to determine whether we're at the end of the list or not. And if we're not at the end of the list, we're going to go back to the top and repeat until we get to the bottom of the list. And once we've completed that, we're going to jump to the bottom and display the prompt. And that'll complete the entire processing of the menu. So let me summarize the entire menu processing engine. There are rules that help the header section determine how it's going to display the header, followed by the header body, which displays the menus on the left-hand side of the screen, and then followed that with the data entry. All these elements are controlled by lists that you create and you can order. They're all controlled by row and column numbers, so it coordinates together. And there's a section for decoding the data so you can decode and display the information you're looking for. So everything that is driven by lists, you can control by adding, subtracting from the list. But the key to all this is to make sure your row numbers align, because that's how things get looked up. And so that you can coordinate those lines together between the data entry section and the body section. One follow-up to all this as I was thinking about it. When you try to debug the lists, it's not that difficult because you can set breakpoints in the different sections. So just as you jump from one list after you've gone through the test to determine you've completed the list, and since everything is row and column coordinated, you can jump from section to section and look at the screen to see that it's coordinated the way you think it's supposed to be. The biggest trouble I had was to make sure the decoders work correctly, that when I built a new way of entering in data, that I went through that process to make sure that it followed correctly through the list, so when I was doing the lookups. Other than that, it's a pretty straightforward menu system. So I want to talk about string storage and where the strings that we've been using throughout the application are stored. If we take a look at the memory map, the entire code space, including memory mapped.io, starts off with 0 and goes to FFFF, with the code portion being from 0 to 8,000 hex. At the bottom of the screen here, I picked two examples of strings. One was the value for the letter A, and the other was the ADC configuration menu text, which are both stored in code space. As you can see from the screenshot, here is where I am using the message letter A in one of the structures. Now you're looking at a common message string file that is where all of the strings are made. And it's made with a macro called make string with size. And I do this so I can get the size and length and the string, and it's going to then store that in the program space. Now we're actually looking at the definition of the macro itself. The first part of this macro creates a constant character with a naming passed in. The second and the key part to this is it's then telling it to store it in program memory. And program memory is code space. And the last part of this macro is where it determines the length, which is using the name passed in, and its length, which is using the size of to determine the length of that string. So later on, if I want to use the length as part of my comparison, I have that available. To summarize, strings are stored in code space. I have special functions that read it from code space into local memory in order to use those variables. I have special code throughout the program like a printf_p, which it knows that that is a pointer that's going to point into code as opposed to pointing into RAM. In this section, we're going to review the reading and writing library that I created for reading and writing to EEPROM. Let's start by filing the DAC initialization code. So we're now in the DAC initialization code, and I'm going to point out the function called DAC reinitialize. DAC reinitialize has a function that's called DAC load config. And so let's jump into DAC load config. DAC load config calls a common function called EEPROM verify signature and load. It passes as an argument to the DAC system, which is an EEPROM location, a index value, which everything but the ADC has a value of 0, and a pointer to the DAC system configuration. Next, we're looking at the DAC save config, which it also passes in a channel number. Again, this one also being used as 0, where the ADC would be a value from 1 to the n number of channels. So as we take a look at this, the top section of this code is designed for you to apply rules to, validate that the changes you've just made fall within some sort of parameters. And each subsystem will have its own set of rules. Then what happens is you're going to go down to this EEPROM write element. Again, you're going to pass in the EEPROM DAC system pointer, the index is 0, and the pointer to the DAC configuration. So how does the library work? Let's take an in-depth look at that now. So there's a section in the flash memory that is allocated for application data called app data. It's 256 bytes in size. I'm going to use that to store our EEPROM data. And so that's really what this library is going to do. So in order to accomplish this, I have a memory map that I'm going to create that lays out each of the subsystems and where they fit into the memory map. I have created a set of 3 different macros. One is to determine the EEPROM size, the EEPROM counts, and the number of elements that are in a particular configuration. Because of the critical nature when dealing with this EEPROM, this is one of the few times I will create blocking code to make sure that something has completed before moving on. As you can see in the initialization code, I have a while statement waiting for the status to complete. It's also in the other sets of code that is related to writing or reading from the EEPROM. What we're looking at here is basically the entire structure that makes up the memory map, including the number of elements and size. That was based on the macros we saw earlier. So when you look at the map, the order of the map that's going to appear in memory is as follows, starting off with ADC, going in alphabetical order down to CZD. So what I did is I started the application and stopped it in the debugger so we could take a look at the memory map. And what you're looking at is the memory map, which is the structure and all the elements in it. And so what we're going to then look at is that each one of those addresses are the addresses in RAM where the pointer is located. And then following it on the far right-hand side is the actual size. And that call corresponds to the structure that we had recorded through all those macros. So one of the values I'm going to use often throughout the EEPROM is this thing called a signature byte. And that signature byte is used to tell me what configuration I am using. And I'm going to use that signature byte, and I'll explain this later in the code, to determine if the size has changed in the elements or the array of configuration data. So how's all that going to work? Well, in the array of elements for the EEPROM was the size of each element that made up a configuration. So the code that you're looking at, EEPROM get address, it takes the index, which is really the offset or the value you're looking for. So if you're looking for the first element, it's going to come in and grab the first element. If you're looking for the third element, it's going to come in and grab the first, second, third element. And what it's trying to do here is to calculate the offset from the beginning of the pointer of the configuration to where the data you're looking for will reside. And this get address function is used in just about every one of the EEPROM functions. So let's take a look at an example of how it's being used. There's 3 values that are being calculated here: base address, element size, and element address. Those are going to be used to determine how much we're going to read from EEPROM. But the very first thing we're going to do as we come down in the code here is, after we've computed all the addresses, we're going to take a look at the data that was passed in, which is a pointer to the configuration that we have. And it's going to compare that to the first byte we read from the EEPROM. And that's where that signature byte is going to come into play. So as an example, let's say you have expanded ADC. The next time you read back the second ADC value, it's not going to match the ADC or the signature byte, and therefore it knows that the value stored in EEPROM is no longer valid. So the end result of that is that since we know it's no longer valid, we're going to write the values from the configuration data that was passed in to EEPROM, and that will fix the EEPROM's data being invalid. And this process will continue through each of the additional loops after this of all the different subsystems, because each one of those will no longer be valid. That way you're not reading back bad data and having the application get messed up because of values have been shifted over. Then we know the EEPROM data is valid. We're going to read the EEPROM data and return that back into the memory location passed in, which is the pointer to the configuration. So essentially we're replacing the memory configuration that was the default values with the new values that were recorded in EEPROM. So I'm drilling into the function a little bit further. In this particular case, it's to read a byte. And one of the things you'll notice is how I convert the address into an EEPROM address with its offset. and you'll see that there is a value called EEPROM start, and that's the physical location inside the microprocessor where the EEPROM's beginning address is. Of course, then you add the offset to it, and that gets you the indent into the location in EEPROM where you want to read the values back. I guess the terms I used weren't as user-friendly as they could be. An element is a byte array that is the configuration. And what this function is going to do is to write 1 byte at a time to EEPROM based on the size of the configuration that was being passed in. So as we drill into the write byte function, you're going to see that I read the byte first and compare the data. And if they match, then I'm going to return. Otherwise, I'm going to verify that the size isn't overrun, and then I'm going to erase the byte, wait for it to be ready, and then write the byte. And the whole reason for doing the verify first is to save wear and tear on the EEPROM, so I'm not constantly erasing and reprogramming that one spot if the data hasn't changed. You'll see that I verify the status, and then I commit the write. So the whole point of that was the blocking code again, where I don't want to move on because of the critical timing that would be involved in the cycle of the writing to the EEPROM. Here's a quick look at the read byte routine, which it also does the same thing of verifying the size is not overrun. It waits to make sure that the EEPROM is ready to be read from, and then the performing of the read. So this completes the quick overview of the EEPROM code, its reading and writing functions, and that how the memory is arranged by the memory map in order to maintain how the data is stored and that it's valid when you go to use it. So in summary, we have completely gone through all the major systems in the demo project for you. The individual systems will be outlined in more detail with debugging overviews and an in-depth analysis of each of the subsystems. Stay tuned for them. They'll be coming in the next set of videos.